So we should be clear what the Clausius-Clapeyron equation tells us. It tells us the saturation vapor pressure. That's the pressure at which the vapor is in equilibrium with the liquid, and the rate of evaporation equals the rate of condensation. So if we started off with a container of ethanol and pumped all the gas away and then sealed the container, what would happen is some of the ethanol would evaporate. And eventually we would reach a point called saturation where the rate of condensation and evaporation are the same. The Clausius-Clapeyron equation would tell us what the pressure of ethanol, the pressure of ethanol is at that point. Now, because that pressure actually equals the ambient pressure above the liquid, this is actually boiling. This would be boiling at 293 Kelvin. But if we had an open container at the same temperature, 293 Kelvin, although this container clearly isn't boiling, because the partial pressure of ethanol is a lot less than the ambient pressure, the Clausius equation still tells us what the partial pressure of ethanol is at that point. Now, the gas right next to the liquid surface will be saturated with vapor, but further away from that liquid surface, say out in the room, the gas could have considerably less ethanol in it. It could just be saturated to a certain percentage. So we have to distinguish between the saturation and the actual vapor pressure. The Clausius equation tells us the saturation or maximum vapor pressure at a given temperature. But of course you can have air that's drier than that. We can introduce phi, the percent humidity. And then the actual vapor pressure of the air can be less than the saturation value. And the percentage phi, or phi is just a percentage of those two, or the actual is a certain percentage of the maximum. And it's the Clausius-Clapeyron equation that tells us what that saturation vapor pressure is at a given temperature. If we look at a graph, then we might be, say, here on a given day. So at some air temperature T, let's extend this line over here. This is our actual vapor pressure. And we see that it's less than the saturation value. So at this point right here, that would be the saturation vapor. That, if you could think of as the maximum amount of, say, if we're dealing with water, the maximum amount of water vapor that air at temperature T could hold. Now, at some higher temperature, which would be 373 Kelvin at STP, the vapor pressure of water will actually reach 101,325, i.e. the water will start to boil in an open container. Another key temperature on here is if you take that air, which is only partially saturated, right, the percentage of the actual vapor pressure, which is from here to here, to the total vapor pressure from here to here, is the percent humidity phi. So, you could sort of look at that and say that looks like about, maybe 75% humidity, because this pressure seems to be about 75% of the saturation. So, one way to reach saturation is to just evaporate more water. Another way is for the temperature to drop. And if this air, say it starts to cool off at the end of the day, then the water vapor in the air is going to start to condense when you reach this temperature. This is called the dew point. So the dew point is the temperature at which water vapor, at some less than saturated value, will actually become saturated and therefore start to condense. So an example then, let's say we had a daytime temperature of 30 C and a relative humidity of 70%. So that's our point right here, right? We're 70% of the saturation value. Then at what temperature, nighttime temperature, would dew start to form? So we'll use the triple point here of 610 pascals and 273 Kelvin. And we just want to find what this dew point temperature is. So during the day, we were at 30 C, or at 303 Kelvin, and it's water, so that's 18 grams per mole, or 18 times 10 to the minus 3 kilograms, and we know the latent heat. I'm about to use the Clausius equation, so that's why I'm listing all of these things. It's 2,256,000 joules to vaporize a kilogram of water. Okay, so First, let's see what saturation vapor pressure would be at 30 C. So according to the Clausius equation, we need a reference pressure and temperature, and we're given those. And then it's E to the minus mu L over R 1 over T minus 1 over T naught. So we're told to use 610 pascals at the reference temperature of 273 Kelvin. And we are at 30 C, so that's 303 Kelvin. And we put in, I'm going to run out of room for the units probably. Definitely won't have room for the R units, and not even for the L units probably. 2,256,000, that's joules per kilogram, and then R is 8.314 joules per mole Kelvin. So basically everything cancels out, and this exponent is nice and dimensionless. And calculating that exponent and then multiplying by 610, we get 3586. So that would be the pressure of water vapor when the air is saturated at 30 degrees C. But of course, the actual vapor pressure on this day is 70% of this, because it's phi times the saturation value. So 0.70 of the 3586 pascals tells us that on this day, 2510 pascals of atmospheric pressure is attributed to water vapor in the air. Now, the air starts to cool. We're going to find the temperature such that this pressure is the saturation value. Because that's what the dew point is. The dew point is the temperature at which the actual vapor pressure becomes the saturation vapor pressure. So, we're going to put this in to the Clausius equation. So this is going to be the saturation value. We'll still use 610 and 273 as our reference, and it's going to be the temperature that's unknown. And so we will again have the same molar mass because it's water vapor, the same latent heat of vaporization, that is a 6, and the same joule per mole Kelvin version of the gas constant. The temperature T is unknown. We're still using the same 273 reference temperature. Okay, so divide, take the natural log of both sides, divide by this, add 1 over 273, and then reciprocate to get the temperature, and it works out to be 296 Kelvin, which is 23 C. So the air would start to condense at 20 when it cooled off from 30 degrees down to 23 degrees. So we were right here on the curve. We had, this was 3586, the saturation value. We were only at 2510 on our 30 degree day, but when it cooled down to 23 degrees, suddenly we hit the saturation curve. That means that the air can no longer contain any more water vapor, and it's actually going to start to condense into liquid state at that point. So that is an interesting start to the analysis we're going to do next in class, because we're going to look at how clouds will form, because as warm, moist air rises, it's going to cool off, and eventually it will reach the dew point. It will reach a saturation, the saturation curve, and that's when clouds will start to form. That's a problem we'll look at in class.